All right, so now we move on to lesson 9.2, part 1, quadratic inequalities in one variable. And this is going to look a little different than our last lesson, which was 9.3, quadratic inequalities in two variables. When we shift our focus from two variables to one variable, what we're going to focus on is, rather than solution regions, now what we're going to talk about is x values that represent the overall situation for where the graph is above the x-axis, below the x-axis, or on the x-axis. So let's see how this looks in this lesson here. Now, starting off with the graph below, they give us some sort of parabolic shape, and they tell us what are the x-intercepts first and foremost of this graph. Now, we could zoom in, and we would see that our x-intercepts are going to be at -7 and 0. That's our first x-intercept. Our other x-intercept is going to be at 3 and 0. Perfect. Now, once we've recorded these, we're just going to make sure we record them in the blank above. So x is equal to -7 for the first x-intercept, and then x is equal to +3. There we go. Now they're going to ask us the following questions. For what values of x is the graph below the x-axis? Meaning, for what values of x is the line below contained here? Well, we would think of this as, hey, if the graph is below the x-axis in this part of the parabola, then it must be that the x values that represent this are the x values that are between here. So it would be between the x-intercepts. And what we're going to do is, because of this, we want to write it as specifically, if it's specifically below the x-axis, then it must be that our left bound is 7, and then it's going to be where x is greater than that -7, but it must be less than 3. Now, I'm going to introduce some color here to represent this. So if the blue represents this part that is below the x-axis, I'm going to highlight that all of these x values would satisfy that, such that if I pick any of those x's that are between, it will represent an x that is where the graph is negative. Okay, now what if we think about the opposite? Where is the graph above the x-axis? It is above the x-axis on the left here, and on the right here. What x values satisfy that for us? Well, if we look at our graph, it would be all the x values that are to the left of -7 and to the right of +3. So what I'm going to use is just another color to shade this, but first let's write out our inequalities. It must be that x is either less than -7 or where x is greater than +3. And I'm going to use green to shade this part here. So green for this solution. I'm going to color this side green, and then I'm going to color my opposite side green. And again, that's because any x value that's on the left or right represents where the graph is going to be above the x-axis here. And we can draw the x-axis right here using a solid red line. The graph is above when we go left and right, and it is below when we're between those x-intercepts. So the rest of the lesson, we're going to think about, first of all, we want to get our x-intercepts. And then once we get our x-intercepts, it's going to define where our graph is either above or below. Really, really important. Now, we could also have the situation where it's equal to 0 and it's right on the x-axis, but those will be our three scenarios. We'll have above, on the axis, which is equal to 0, and then below, which is going to be for all our y values that would be below the x-axis. Now, let's take a look at this piece here. So use the graph that was given above to solve the inequalities. Show your solution on a number line. Now, where is it that this overall function is less than 0? We said that it was between those x values. So right away on the above graph, just as we've discussed, where it was less than 0 was when it was between 7 and 3. And if this is the case, then what we're going to do is we're going to draw out our number line. So here's our number line, and I'm going to write that we have -7 on the left-hand side, 3 on the right-hand side of this number line. And then because it is a strict less than, we're going to use some hollow dots at this point. So hollow dot, hollow dot. And then because it must be between these values, I'm going to connect them with a line. There's our number line. So a hollow dot, remember, represents that it's less than or greater than, but not equal to. Okay, where was it greater than or equal to 0? It was greater than or equal to 0 when it was outside. So we're going to write it as, first of all, x was less than or equal to -7, and then x was greater than or equal to 3. And what we're going to do is on this line, we're going to make sure we use solid dots, and we're going to write it in the following way. Again, it's going to have our 7 on the left-hand side here, our +3 over here. We're going to put a solid dot on 7 because of the equals, a solid dot on 3 because of the equals, and because it was above, or it was positive in these regions in which it was to the left and to the right of -7 and 3, we're going to draw an arrow that goes left and an arrow that goes right. Lastly, where is it not equal to 0? Well, the only points in which this is equal to 0 were specifically at the x-intercepts. So as long as we don't include these x-intercepts, everywhere else it's not equal to 0 overall. And so what we're going to do is we're going to write this as the following. As long as it's x cannot equal the -7 or x cannot equal the +3, we're good. Let's represent this on a number line here. We're going to put in the following. This will be -7 here. This will be +3 here. We're going to put hollow dots at these points because we don't want to equal at those points. Then what I'm going to do is put an arrow going left, a line that connects the 2 points, and then an arrow going to the right to infinity, representing that it can be any other value other than -7 and 3. Now, what you're going to notice about this lesson is when we talk about it in one variable, just as we've talked about on the earlier part of the lesson here, or in the introductory, we want to notice that there's only one variable being discussed in this inequality, and we want to describe our solutions or the possible values only in terms of x, because whatever these x values are, they determine, are we above the graph? Are we in the positive, Are we in the negatives for the y values? Are we above the x-axis, below the x-axis, or even on the x-axis, as we've seen in the above example here? Now, let's discuss the different methods in which we can figure out what are these given x values, or what are the possible x values that can represent these inequalities. Starting off with the graph method. To graph these, we want to rearrange any inequality such that we have one side equal to 0. Really, really important. And most often, the right-hand side is going to be 0. The other thing we want to do is find the roots in our calculator. So we're going to do our second trace zeros, or even on the Casios, shift G-solve roots, and we're going to be able to figure out what these x-intercepts are. Okay, let's do that here. So we're given the overall quadratic below, and this is some sort of quadratic inequality that's less than or equal to 0. In your graphing calculator, I want you to type in y1 is equal to x squared minus 10x plus 16, just as you see here. Now, we don't need to do any readjustment because it's all on one side, so we're good there. So let's write out our TI instructions. In the TI calculator, you're going to go second, you're going to then go trace, and then you're going to go 0. If you do second trace 0, you'll do your left and right bounds, and you'll be able to find these x-intercepts. For the Casio, what we want to do is we want to do shift, G-solve. Once we G-solve, then what we're going to do is click the button root. Now, when we do this, we're going to figure out that x is equal to +2 and +8, meaning that when we look at this, we want to make sure we draw out a sketch now that we have our x-intercepts. Given the following window, and I'm going to give you some window settings you can type in, I'm going to adjust the window to 0 for the minimum for x, 10 for the positives, and then 1 is the scale. Again, we don't want to adjust the scale if we don't have to. In terms of the y's, we're going to make it -10, 10, and 1, and close the bracket. And here's what this graph is going to look like. Our y-axis is going to go right on the left. We're going to draw our x-axis kind of right down the middle here. I'm going to make sure I sketch in the overall parabola, or generally what the parabola looks like. So using this, let's see if our tool will make this work here. There we go. Yeah, seems good enough for us. You'll get something like this. You're going to put a dot here on these two x-intercepts. And then what we want to do is we want to write in the following. It's going to be, the first one was 2 and 0. The second one was 8 and 0. Excellent. Now, we want to make sure that when we look at this and we talk about the solutions to this, what we need to be thinking about is, how does the inequality reflect what our answer is? Well, if we know that this quadratic inequality is less than or equal to 0, it means that these values are going to be included. And then on top of that, we want to figure out, where is the graph below the x-axis? It's below the x-axis right here. And if that's where it's below the x-axis, the x values that represent this are the following: between 2 and 8, including 2 and 8. So we're going to say, therefore, in a solution here, and maybe we'll do, just off to the side here, this will be more than enough. Therefore, we're going to start with our lower bound of 2. If x must be greater than or equal to that 2, and then less than or equal to the 8. And this represents the solution region where the graph is less than or equal to 0. Very, very important there. Okay, so that's one method, is graphing. And this isn't algebraic, it's it's the graphical method where we type it into a calculator and we use the calculator to figure out all these values. Now, let's look at some algebraic approaches. Method 2, the root and test points / the sign test. And this is considered to be our first algebraic approach that's available. Now, to do this, what we want to do is, again, we want to rearrange the inequality so 0 is on the one side, specifically on the right, typically. We then want to find the roots by factoring or using quadratic formula, which is an algebraic way of factoring. We're going to then place the roots on a number line from lowest to highest and then split it into the different intervals. And then finally, we want to select some points that go between those intervals such that we can figure out what the sign is or if the inequality would be true in those given regions. Now, that's a lot of word salad in terms of if I read out those instructions without an example, sometimes it's a little bit tough to track. So let's put this to work here. Here is the inequality they give us. X squared plus 2x minus 24 is less than or equal to 0. What we want to do is we want to figure out the roots of this. Right away, we're going to factor this. We know we have to multiply to make negative 24 and add to make positive 2. The numbers that do this for me are x plus 6 and x minus 4, which will be less than or equal to 0 here. Or in this case, because we're trying to figure out the x-intercepts, I mean, yeah, let's keep the inequality in there just because we're going to use this inequality. If I was to separate these into the two x-intercepts, we know from our quadratic equations unit, we would take these binomials, separate them, isolate them for 0, or we could just recognize that if it's positive 6 in the brackets, it's negative 6 outside the bracket, and if it's positive 4 inside the bracket, or sorry, negative 4 inside the bracket, it becomes positive 4. So our two x-intercepts are going to be negative 6 and 4. Now, this helps us determine these intervals because now we have a left and right bound, or a left and right intercept. So I'm going to write it as our first interval is where it's less than this negative 6. So any value that's less than this negative 6, we want to test. We then want to say negative 6 is less than x, which is greater than that negative 6, but less than 4. We want to test a value between our two x-intercepts. Lastly, we want to test a value that is to the right of our farthest right x-intercept, which is 4. So we're going to say we want the interval where x is greater than 4. Now, we don't want to put equals or else this will cause this to become 0 and it will be on the x-axis. So, I mean, realistically, our end solution is going to include the equals in here, but we want to test specific points that are not these x-intercepts and rather points that exist to the left and right or to the adjacent of these. Now, I'm going to use some values here. Suppose I pick negative 7 in this first one. And then suppose I choose 0 because 0 is between a negative integer and a positive. And then let's say I choose 5 for this one. I choose the closest values that are just beyond or kind of right in the middle of these bounds. In the root and test point method, now we have to substitute this into the inequality and see if this actually holds true to it being less than or equal to 0. So let's do that. In the first bracket, I'm going to take negative 7 and add it to 6. In the second one, I'm going to take negative 7 and then subtract 4. Well, here's what the value becomes. Negative 7 plus 6 is equal to negative 1. Negative 1 times negative 11, this ends up giving us positive 11. This is greater than or equal to 0. In this specific case, it's actually just strictly greater than 0. We don't want to say equal to. So if we know that this is greater than 0, does it satisfy that it's less than or equal to 0? Absolutely not, because this is a positive value. So we're going to say no. Okay, and even if you wanted to, what you could do right below is just say, hey, this ends up being positive, and if it's positive, it's definitely not less than or equal to 0. All right, we're going to go to where it's 0. I'm going to plug 0 into the brackets or into the original inequality. It gives me 0 plus 6, and then 0 minus 4. This is the same as saying 6 times negative 4. 6 times negative 4 is equal to negative 24. And negative 24 is less than 0, meaning it's a negative value. And if it's negative, it definitely is less than or equal to 0. So in this portion where we say, hey, does it satisfy it where it's less than or equal to 0? Yes, this value does. Okay, we're going to go over to where x is equal to 5. I'm going to plug it into brackets. 5 plus 6 multiplied by 5 minus 4. This is going to end up giving us where it is 11 times the positive 1. 11 times positive 1 is 11. And again, this is greater than 0. If it's greater than 0, that means it's positive. And therefore, well, 11 inherently is actually positive. And then we look at this and say, no, it does not satisfy the inequality. That means it has to be less than or equal to 0. So because this is positive and it's greater than 0, we don't want to consider this region. Now, what does this mean for our solution? we have to wrap this up and say, okay, well, our solution is therefore the following. And we're going to make sure we write it in maybe the space right below here. I'm going to take this quadratic inequality and write it again. X squared plus 2x minus 24 is less than or equal to 0 when we want to reflect on when it's less than or equal to 0. We found that it was only in the middle region being between 6 and 4, more specifically -6 and 4. So this inequality is less than or equal to 0 or negative when -6 is less than or equal to x, which is less than or equal to +4. This is how we would summarize our solution for these types of problems. We want to define the regions in which, or the specific x values that demonstrate that this inequality would be less than or equal to 0. Okay, now what we're going to do is we're going to do the alternative method, which is the sign analysis. Sign analysis is basically the same thing. It just looks a tiny bit different in its overall construction, but it accomplishes the exact same thing here. So what we're going to do is we're going to take this exact same inequality, the x squared plus 2x minus 24 is less than or equal to 0, and we found through this solution here that our roots were the following. We had where, first of all, it was x plus 6 for one of them. We then had our other binomial, which was x minus 4. And then we had the combined binomial, or the combined expression of x plus 6 and x minus 4 must be less than or equal to 0. That was the factored form of our trinomial. And if we wanted to, we could even write the original trinomial of x squared plus 2x minus 24 is less than or equal to 0, just to make sure that we see them as the same thing. What we're then going to do is we're going to create our t-table. So I'm going to create this big table, which then we can fill in specific values for. And make sure you go all the way to the top here. And then what we're going to do is we're going to create a series of 3 columns. So there's 1 column, 2 columns, and 3 columns. And what I'm going to do is I'm just going to erase out all of the other detail here. So I don't really need any of the parts on the bottom here. I don't really need any of those parts on the right that was extra. Now, what I want you to do in sign analysis is I actually want you to do the following. And we're just going to move this down just a touch so that we can fit the values I want above. In the beginning here, we know our roots were -6, which is here, and then we're going to put +4 here. I'm going to put my x-intercepts along the column lines or along the column divides, because what I want this to look like is my x-intercepts are along these lines, and then the values that we're going to test in here to complete the sign analysis will go on those lines. So here's what we're going to do. We're going to use the same values, -7 here. We're going to put 0 between, and then we're going to put 5 on the value that is greater than 4. So all of these values are values that we've picked that are between those specific regions. Now, one by one, we're going to plug this in. So if I plug in -7 to the x plus 6, I'm going to get -7 plus 6. This gives me a negative. If I plug in a -7 to x for x minus 4, this is also going to give me a negative. Therefore, a negative and a negative will make a positive when you multiply them together, because that's technically what we're doing. We're taking the binomials and multiplying them together. If I put in 0 for x for the next one, it's going to be 0 plus 6 is +6. 0 minus 4 is negative. A positive and a negative make an overall negative. Lastly, if I take 5 plus 6, that's a positive. 5 minus 4 is +1. Therefore, this is a positive. The region that describes where it's less than or equal to 0 is the negative region where it's between these x-intercepts. So therefore, we would summarize the solution and say x squared plus 2x minus 24 is less than or equal to 0 when the x values are between -6 and +4, including the 6 and 4. Perfect. And again, the way you can determine if it's a equal to or if it's just a strict less than or greater than is whatever is in the original inequality is what you see in your answer. So I just want you to be very careful with that. If you see this, you'll also see it in your answer like this. Okay, now when we zoom out on this problem, what you're going to notice is that whether I use the root and test point or I use sign analysis, hey look, it shows the exact same thing. We see an area which is negative that is defined by a specific interval. I would say that the root and test point and the way they organize it in this table is somewhat neater for sure. So if you're one of those people that really requires a neat solution, I think that root and test point will be perfect. However, If you realize what's happening in sign analysis, you're going to realize it's actually just the same thing. It's just truncated a little bit. And what I'm going to encourage is that sign analysis is used heavily in calculus or math 30-1, not 30-1, but math 31. So if you're one of those people that eventually will take calculus, sometimes getting used to sign analysis is nice because we're eventually going to do points of increase and points of decrease in calculus, and it might be more important to see it long term in this way of sign analysis. But again, these are both algebraic. They both represent the same information. So pick one, and as long as you're good with one, that will be good. You might have to demonstrate one versus the other, so know how to do both, but definitely build comfortability around one or the other. All right, now moving on to case number 3, or method number 3, not case number 3. This is our other algebraic approach. So we have root and test point / the sign analysis. The other algebraic method is the case analysis. Now, case analysis relies around us looking at the problem from a slightly different lens, and that's this here. If we know that we have a certain inequality, specifically, if we have an inequality where the inequality is a greater than or equal to or a strict greater than 0, what we need to realize is that in order for something to be greater than or equal to 0 or greater than 0, either both factors must be positive, because a positive times a positive would give us a positive value greater than 0, or we would have where both factors are negative, because a negative times a negative gives us a positive. And again, if we want to show this off to the side, we could. So a positive times a positive will equal a positive. A negative times a negative will equal a positive. We can easily show that this will both result in a situation where it's either greater than or equal to 0 or strictly greater than 0. Okay, that's the case where they're greater than 0. They're either both have to have positive factors or both have to have negative factors. In the opposite case, what if we see a situation where we know that it is going to be where it's less than 0 or less than or equal to 0? This happens when we have the following situation. Either the first factor is positive and the second is negative, or this first factor is negative and the second is positive. Using some symbols here, let's do that off to the side. The first factor is positive, the second is negative. This will equal a negative, or something that's less than 0. The other situation is where it's negative times a positive, which will give us a negative. And in both situations here, we realize that this will be less than or equal to 0 or less than 0 because it's representing a negative value. Now, again, some of this can get really caught down in the instructions or bogged down in the instructions. So what we want to do is we want to apply this right away into some examples here. Let's look at the sign analysis, or not the sign analysis, but the case analysis around this quadratic inequality. Now, step number 1 with quadratic inequalities is to always factor them, because unless we have them in the factored form, we don't know what the two binomials are, or we don't know what the factored form is that represents the x-intercepts coming from them. So to do this right away, what we're going to do is we can create a little x in the top and be like, we must multiply, and I'm going to make that a little neater. We must multiply to make negative 24, which is the outside term, and add to make the negative 5. The two terms that do this for me are 8 and positive 3. And because the coefficient of x squared is 1, we can do inspection, and we can actually say that this will end up factoring to be x minus 8 times x plus 3. And this is where it's less than or equal to 0. So here is our inequality that we can use. Now, if this is something where it's less than or equal to 0, that means we have it where the y values, or the graph, is going to be negative. And when the graph is negative, one of these binomials has to be negative in order for this to be true, / less than 0. So for case 1, let's do the following. We're going to take x minus 8 and set it so that it is positive or greater than or equal to 0. In the other situation, we need to make it such that x plus 3 is less than or equal to 0. So this one is going to be our positive, this one's our negative. Let's solve the inequalities. We add 8 across, this gives us x is greater than positive 8. For our other one, it's x is less than negative 3. We want to draw out two different number lines for this. So here's our first number line, here's our second number line. Make sure we put arrows on the end representing that these continue left and right to infinity. On both of them, we're going to put our negative 3 here on the left-hand side of the number line. On the right-hand side, we're going to put 8 and 8. And now what we want to do is, because we're going to represent the first situation where x is greater than 8, we're going to put a solid dot because it's an equals to inequality. And it's going to go to the right because it is where it is greater than or equal to 8. In the other case, it was where it was less than or equal to -3. So we're going to put a solid dot and then an arrow going left. Now, what you're going to notice is, hey, look, they don't have any crossover. These red lines never overlap each other. One of them is going to positive infinity, the other one's going to negative infinity, and they're separated by a total of 11 units. So there's never going to be any crossover. Therefore, we got to move on to case 2 because this didn't give us enough information. Now, in case number 2, we're just going to flip the inequalities and make the x minus 8 the negative case, or where it's less than 0. So it's going to be x minus 8 is less than 0 instead of greater than 0 this time. There we go, less than or equal to 0. And then we're going to set our x plus 3 such that this one is now greater than or equal to 0. Isolating it for x, we're going to get x is less than or equal to 8, and x is greater than or equal to -3. Drawing out our two number lines, just as we've done in the case 1, we're going to have it where it has the arrows on the end going to infinity. We're going to draw our -3 on the left-hand side for both of them. We're going to draw our 8 here for both of them. And then now we're just going to do them one by one. Where x is less than or equal to 8, that means that it is going to be an arrow going to the left with a solid dot at 8, representing that it's included. And then for my second case here, or for my second part, we have it where we put a solid dot on 3 and an arrow going to the right because it's greater than or equal to that 3. Now, what you're going to notice is that there's an area of overlap. This area of overlap is what we call our solutions. So what we're going to do is we're going to put this as a dotted line. I'd recommend you use some sort of highlighter or something. And we're just going to put a dotted line going up, and we're going to say that this represents the solution. Perfect. Now, if this is the solution, we want to say, because this is where the two overlap, this is going to represent the x values that satisfy this inequality. We can now go below and wrap this all up and say, therefore, the x squared minus 5x minus 24 is less than or equal to 0 when the x values are between -3 and +8. So as long as it's between these values, we can say, therefore, the inequality is satisfied and that the graph would be less than or equal to 0 at that specific interval of x. So very, very important. We're thinking about this all in terms of what x's will satisfy this being less than or equal to 0 or greater than or equal to 0 or even 0. In this specific situation, we wanted it where the graph will be below the x-axis. Awesome. So this is case analysis. We've seen it in this situation. We're going to deal with one more of each of the types, so don't you worry. We're going to see this all again one more time. Now, let's flip the page here, and we're going to repeat all these things in terms of we're going to do one graphical example, we're then going to do one root and test point / sign analysis example, and then we're going to do one more case analysis, and then we'll move on to some more complex problems. But for now, we want to do one more of each just to make sure we're okay. Okay, starting off with the graph, we know we need to make sure it all equals 0. So I'm going to start by saying y1 is equal to, in order for this to all be equal to 0, we are going to subtract 10 from both sides, and this is going to give us a new inequality of x squared minus 4x minus 10 is greater than 0. We've isolated one of the sides for 0. If the x squared is positive, we're happy with this too. So in your y1, I want you to type in x squared minus 4x minus 10. We're then going to figure out what our x-intercepts are using our graphical commands. Our x-intercepts are going to be where we have x is equal to -1.74 and where x is equal to 5.74. Now, let's just make sure we sketch this out on our graph here. Off on the right-hand side, I'm going to draw a very rough parabola that demonstrates this specific thing. So cuts below, goes through 5 like this. This might be good enough for us for now. Maybe it's not exactly perfect, but if we put arrows on the end, we're going to write in the following. We always in this unit want to write in our x values here, or specifically our x-intercepts. And at these x-intercepts, we may as well even put hollow dots because we know strictly at these x-intercepts, these aren't going to be included in the graph points. So we want to be specific about that and be like, if they're not going to be included, let's put some hollow dots. Now, from here, if we know these are hollow dots, where is the graph greater than or equal to 0 on this graph? It's greater than or equal to 0 for all x values that represent this and this arm, which means that if we highlighted this on the x-axis, it's going to be all of the points to the left, all of the points to the right-hand side, and this will represent all the x values that are positive for the overall graph. or that make the graph positive. Okay, so now let's define this. We want to always make sure if it's a graphical solution, that we write in what our x-intercepts were. This is negative 1.74 and 0 for the first one. The one on the right was 5.74 and 0. The other values we don't care about, so we don't need the p and q value, aka the vertex. We don't need the y-intercept. As long as we have our x-intercepts, we're happy. Now what we're going to do is we're going to say, if we summarize this, therefore x squared minus 4x minus 10 is less than 0, or sorry, greater than 0, because we're talking about where it's above the x-axis, when either x is less than, and specifically we need to make sure it's just less than negative 1.74, or where x is greater than 5.74. Now, what you're going to notice about this is, again, whatever our original inequality was, do you see how it was a strict greater than? That means that we used strict inequalities in our answer. If this included an equal sign, then our end solution would also include an equal sign. But because it's a strict inequality, it's strict and strict here. And we wanted to make sure we reflect it as hollow dots at those x-intercepts, because they're not actually going to be included in this specific value, because we want it only where the graph is above the x-axis, not including the x-axis. Okay, let's move on to our next example, which is going to be the algebraic approach, or the first algebraic approach. We want to use the root and test point / sign analysis method. Now, again, what we have to do is we have to start by taking this, and we're going to rewrite it, less than 7x plus 4. I'm going to take all of the stuff on the right and move it to the left-hand side. So when we move it over to the left-hand side, this is going to give us 2x squared minus 7x minus 4 is less than or equal to 0, because we keep the inequality facing the same direction as it originally was. Now that we have the trinomial on the left-hand side, let's factor this thing. So we're going to draw our x over here, and in this case, we need to use decomposition. 2 times 8, or 2 times negative 4 is negative 8. We must add to make the negative 7 in the middle. The two terms that do this for me are negative 8 and positive 1. I'm going to now do decomposition by writing 2x squared minus 8x plus 1x minus 4 is less than or equal to 0. From our factor unit, or chapter 0, we group the first two, group the second two. We factor out the 2x, leaving us with x minus 4. We can only take out a positive 1 from my next grouping, leaving us with x minus 4. We see the common binomial. I'm going to take the outside terms of 2x plus 1 and pair them. I'm going to take one of that common binomial and write it, and this is all less than 0. Now, what are our x-intercepts? We could take this by quad equations unit. We would get negative 1/2, and we would get x is equal to positive 4. These are the two x-intercepts that represent the x-intercepts on our graph for this. Now, using this allows us to build out our table for the root and test point / sign analysis. Now, I'm going to approach this from a more sign analysis based approach. I'm going to build out the table, and I'm going to start by writing out the first factor. The first factor was 2x plus 1. The next factor was x minus 4. And then we want to combine them together and write it as x minus 4 times the 2x plus 1. And again, you can exchange that order. It really doesn't matter if we swap the order. I'm even going to write the original quadratic here. So 2x squared, and then minus 7x minus 4 is less than or equal to 0. Now let's create our table here. With this piece, we're going to draw a line across, line across, line across, and then one along the top. For this, we want to create 3 columns. So 1, 2, and 3. I'm going to shave off just any of that excess in terms of the excess lines here, just to kind of tidy it up a tad bit here. So we don't need any of the parts on the bottom here. Just going to wipe those out. We don't need this. There we go. Now what we want to do is, on those lines that represent the column lines, we're going to put our x-intercepts. So the first x-intercept was negative 1/2, which I'll put here. Our second x-intercept was at positive 4, so I'll put that here. And now what we want to do is select some values that we can test in these binomials and see if it's less than or equal to 0. So if I want to pick a value that's less than negative 1/2, let's pick negative 1. If I want to pick a value that's between negative 1/2 and 4, we're going to pick 0. And then a value that's greater than 4, let's just pick 5. Now, going one by one, here's what we're going to do. We look at this and we say, if I plug in negative 1 to the first binomial, negative 1 times 2 is negative 2, plus 1 is a negative. Negative 1 minus 4 is also a negative, meaning this interval is actually a positive interval, or it's where the y values or the graph is all above the x-axis. All right, let's plug in 0 to both. 0 times 2 is 0, plus 1 is positive. 0 minus 4 is negative. This will give us a negative region. If we plug in 5, 2 times 5 is 10, plus 1 is 11, so this is a positive. 5 minus 4 is positive 1. This gives us positive. Therefore, the overall region is going to be positive or above the x-axis in terms of the graph. The only spot in which the graph is less than 0 or equal to 0 is when it's between these x-intercepts. So let's summarize this as a solution. Therefore, the 2x squared minus 7x minus 4 is less than or equal to 0 when it is between those x-intercepts of negative 1/2 and 4. And again, do you see again how we look at this and we say if our inequality included or had the equal sign, then our answer will also have the equal sign. That's immediately how you know. You base it on the original inequality you were given, and that will tell you a lot about what your solution should have in terms of the signs of the inequality. All right, now we've done a graphing situation again. We've done one that was the root and test point / sign analysis. Let's do one more case analysis example. So again, they give us a quadratic inequality such that we have to actually do a little bit of work to start the problem because it's not isolated in terms of one side being 0. So we're going to take 3x squared, and then which is greater than 7x plus 6. We're going to subtract away all the stuff that is on the right-hand side and bring it over onto the left. When we bring it over onto the left, this is going to give us 3x squared minus 7x minus 6 is greater than 0. Again, we don't flip the inequality unless we've divided or multiplied by a negative, which we definitely have not. Now what we're going to do is factor this off on the side. We need to multiply to make 3 times negative 6, which is negative 18. We need to add to make negative 7. The numbers that do this for me are negative 9 and 2. Now we need to use decomposition. 3x squared minus 9x plus 2x minus 6 is greater than 0. We factor by grouping from chapter 0. We're going to remove out 3x, which leaves us with x minus 3, plus 2, which can factor out of the second grouping, leaving us with x minus 3, and this is all greater than 0. We're going to take our outside terms of 3x plus 2 and pair them, and one of our common binomial, x minus 3, which is greater than 0. Our x-intercepts are going to be where x is negative 2 over 3, and where x is equal to positive 3. There we go. And again, that comes from our quadratic equations unit, where we took each of these binomials and then isolated them for x. So if you don't believe me, take some time and just do those algebraically, but you'll eventually get so good that you'll be like, oh, if it was positive in the bracket, it's negative here, and that's my term. If it was negative, now it's positive. You'll get really good at these. Okay, let's do our case number 1. Before we do that, if it's greater than 0, either both factors must be positive, because positive times a positive would end up giving me a thing that's greater than 0, or they're both going to have to be negative, because a negative times a negative gives you a positive or something greater than 0. So let's break down those cases over off on the right-hand side here. Case number 1. We're going to have where we have 3x plus 2 is greater than 0, and then our other one is x minus 3 is greater than 0. If this is the situation, we're going to isolate for x by subtracting the 2 across, which is giving us 3x is greater than negative 2. We divide both sides by the 3 here, and when we divide both sides by 3, we end up figuring out that x is greater than 2 over 3, or more specifically, negative 2 over 3. If I add 3 to both sides on my second inequality, it's going to be where x is greater than 3. Now let's write this out using 2 number lines here. So just like we did in our first example of case analysis, we draw out our 2 number lines. We then put in our negative 2 over 3, which was our first x-intercept. And I'm just going to make sure that 3 is just a bit better. There we go. And negative 2 over 3. We put our positive 3, which is our positive x-intercept. And now we want to use some number lines to represent this. If it is strictly greater than negative 2 over 3, hollow dot, and then put arrow to the right, representing that it's all the values that are more positive or greater than this, but not including it. For my x values, what we're going to do is it's greater than 3, but not including. I'm going to put a hollow dot at 3, and if it's greater than 3, we arrow over here. Now, here's what you're going to notice. Look at what we've just created. When we've created this inequality like this, we see that as long as it goes past 3, it can go to positive infinity, and they share a solution here. So there's one solution region, and we'll talk more about this as a final answer in a second. We want to do case number 2 just to make sure that we get all possible x values. So let's just make sure I move this over as much as humanly possible, because we're going to want to have as much room to work with as we can. Let's take out any excess there. Okay, for case number 2, here's what we're going to have. Case 2. If in the first situation, or the first case, they were both positive, now I'm going to make it where they're both negative. 3x plus 2 is less than 0, and x minus 3 is less than 0. Apologies for making this squishy. If I isolate this, it's going to isolate the same way. I'm going to go 3x is less than negative 2. We're going to divide it both sides by 3, meaning that our inequality is going to be x is less than 2 over 3 negative. For our second inequality, I'm going to add 3 across just as we've done. This is going to give us x is less than positive 3, and now we want to draw it out on the 2 number lines as we've done before. So here's the 1 number line, and then here is our other number line. We're going to make sure we fill in our values. So this is negative 2 over 3, negative 2 over 3. This is where it is positive 3 and positive 3. Now what we're going to do is we're going to make sure on this number line, we sketch the first situation where it's less than negative 2 over 3. That means I'm going to put a hollow dot and then an arrow going left. And then for 3, I'm going to do the same thing. If it's less than 3, hollow dot, arrow going over this way. And what I notice is I've created another solution region. Put dots on the endpoint here, dots on where they first cross over. These are what we're going to call our solution areas or solution regions. So I'll even put that this is going to be the solutions, and I'm going to arrow up into this part. I'm going to arrow up into this part. Our last piece here is to just summarize what these actual regions are represented by in terms of inequalities of x. So therefore, our solution is going to be 3x squared plus, or not plus, but minus 7x, and then minus 6 is greater than 0 when we have x less than negative 2 over 3, because we found in the first, or in that second case, anytime it was less than 2 over 3, there was an overlap of the 2 lines. There was red lines going in the same direction. The other situation was where they were both greater than 3. And so we're going to look at this and say, or x, and I should say probably and would be more appropriate here, and where x is greater than 3. There we go. There's our solution. And again, in our original equality, if this thing had a strict inequality being greater than but not equal to, then our answer should also include that in terms of the regions in which this is true. All right, perfect. So case analysis is a really beautiful tool. It is algebraic, so if you want to use an algebraic method and they just give you the option to use any algebraic method, this does work. You can use this method. However, I think just like I've said before, in calculus, you're going to deal with a lot more of the sign analysis method. And not that you don't do some sort of form of case analysis in calculus as well, but in terms of the sign analysis, I really like it as kind of like an entry to further math courses. But again, both are algebraic. Both are totally valid. I would actually practice a bunch of both and then make an executive decision of like which one you kind of like better. But being able to use both is never a bad thing by any means. Okay, now let's go into our final 2 examples for the class. So first of all, we're going to deal with one where we have some sort of rational expression where we have a fraction in this, and we want to get rid of these fractions because I don't know about you, but I hate fractions. I want to get rid of these things because we want to deal with more normal trinomials. So what we got to be thinking about is what is the lowest common multiple, or the first number that both 3 and 5 would reach? Simply put, we just multiply them together. This will give us an answer of 15. So if I multiply my left-hand side of the equation by 15 and my right-hand side of the equation by 15, what this is going to allow me to do is I can then get rid of the denominator for both of these two. And I'm just going to move this up and then just arrow down to it, representing that we're using an LCM here. Okay, let's continue this work just off to the left-hand side. If I multiply them both by 15, 15 divided by 3 is 5. So for our first term, it's going to be 5x squared. We're then going to take 15 and divide it by 5, which is 3. 3 times 2x gives me 6x, which is less than 1 times 15, which is 15. Again, we don't like this where we have some sort of piece that is on the left hand or on the right hand side. We want it all to equal to 0. So I'm going to subtract 15 from both sides. this is going to give me 5x squared plus 6x minus 15 is less than 0. Okay, now that we have this all equal to 0, what we can do is we can type this into our graphing calculator. Y is equal to 5x squared plus 6x minus 15. If we type this into our graphing calculator, we're going to figure out that x-intercepts are located at the following 2 points. And let's make sure I can write this out here. X-intercepts. The first x-intercept is where x is equal to negative 2.43. The other x-intercept is located at 1.23, but positive. Okay, now I'm going to give you some window settings in which we can put this into our graphing calculator here. So off on the side, I want you to put the following window settings. We're going to adjust it so that it's -5, 5, and 1 for scale for the x values. For the y values, we're just going to keep it a pretty actually, no, we're going to adjust the minimum a little bit. We're going to make it -20 for the minimum. We're going to make it +10, and then a scale of 1. Now, here's what the graph is going to look like. We're going to have a graph where it's shifted up a little bit in terms of the x-axis because we're looking a little bit lower on the x-axis. We're going down to -20. In terms of the x values, it's equal on both sides. So we're going to draw the line right down the middle. I'm going to draw some sort of parabola that could represent this. It's a little further on the left than it is on the right-hand side. So roughly, this is kind of what we should get with the arrows on the end. And again, what we want to do is we want to make sure we label our x-intercepts, and I'm going to make sure that they're both hollow. So hollow dot and hollow dot. The reason they're hollow is because this is where we're looking, where it's less than the 0. We want it strictly less than 0. The graph is less than 0 anytime it's in this region here, or anytime it's between, but not including those x values. So let's make sure we write this out here. Our first x-intercept was -2.43 and 0. Our other x-intercept was 1.23 and 0. And if these are our two x-intercepts, the solutions for where the graph is less than 0 or below the x-axis is the x values that are between these two, but not including. So we're going to highlight that piece there. And now we're going to summarize this as a final answer. If this is what we ended up getting graphically, that those are where it satisfies it for being less than 0, we want to say, therefore, 5x squared plus 6x minus 15 is less than 0 when, and we're going to write it just below here, x is -2.43. Whoops, there we go. X is greater than 2.43, but less than 1.23. There we go, and that's our solution there. Perfect. And it's not going to include those x values, because if it included those x values, then that would be saying that it's less than or equal to 0. Again, we always look to match our solution to the original inequality. So if it's a strict less than or equal to, or a strict greater than, and I shouldn't say less than or equal to, if it's a strict less than 0, then it must be that we're seeing strict inequalities in our solution. Same thing for, like, if it's a strict greater than, we would see strict inequalities here. All right. Final example for class is a little bit of a tough one because it gets us to consider things from the polynomials unit of Math 30-1, kind of in that style. We're going to be given a polynomial that is a cubic function. Now, this is where it gets a little difficult, is we want to look at this and be like, traditionally, we want to factor these things, right? But we see an issue. If this is a cubic function, then we can't factor this. We can't use our standard, hey, what multiplies to make the outside adds to make a middle. Before we do that, we know step number 1 in factoring is to always take out a greatest common factor. So let's take out a greatest common factor. In this case, they all share at least one x. I'm going to write this as x times x squared minus 3x minus 10 is less than or equal to 0. Hey, now we have that trinomial that we can factor. Off on the side here, what I'm going to do is I'm just going to create that x that we can use. So we're going to create our x and say it multiplies to make -10, adds to make -3. The values are 5 and 2. Now plugging that in, because we can use inspection, it's x minus 5 and x plus 2 is less than or equal to 0. From here, we would know our x-intercepts are going to be the following. X is equal to 0, x is equal to +5, x is equal to -2. These are all the x-intercepts. Now, one thing I want you to highlight in your notes, or even just underline here, is this x. It is very, very important to keep this x. We do not want to just divide it to both sides like we sometimes did in quad equations with common factors. this is not just a numeric coefficient. In fact, it is a variable that represents an x-intercept. This represents some specific x being placed into this overall equation. So, or into this inequality even for that matter. So we don't want to just get rid of x. It's not just a generic coefficient, it is a specific input value. All right, now we see this as our 3x-intercepts. So therefore, if we want to do our sign analysis on this, we're going to create a table below, and I recommend that we start by writing out what our factors were. So we're going to have x for our first one, we're going to have x minus 5 for the second, we're going to have x plus 2 for the third one, and then we want to write them all together. So it's going to be x minus 5, and x plus 2 is greater than or equal to, or sorry, less than or equal to 0. It's the opposite direction. Less than or equal to 0. The original polynomial was x cubed, and then minus 3x squared, then minus 10x was less than or equal to 0. The reason I like to write both the factored form and the original is that we use the original in the solution, so it's good to just keep track of it. Now we're going to create our table just as we've done before, but there's going to be a sharp difference that I'm going to point out in just 1 second. So because we have 3x-intercepts instead of 2x-intercepts, now what we actually need is 4 positions. So we're going to do 1, 2, 3, and 4. And then again, just like we've done, we're going to trim off that excess that we don't need under this piece here. And the reason we need to create 4 for this is that we now have 3x-intercepts, meaning we need 3 column lines that represent the x-intercepts, such that we can create the appropriate regions. So under the first one, we're going to write it as our lowest x-intercept. Our lowest x-intercept goes here, which was -2. Our next lowest was 0. Our greatest was +5. Now, let's pick a bunch of values that exist to the left and in between these values and then to the right of 5. Something that's to the left of -2 is -3. Something between -2 and 0 is -1. Something between 0 and 5 is 1. And then something greater than 5 is 6. All right, let's go one by one and just plot these out and see what we get. So first of all, if x is equal to -3, this is negative. If we plug in -3 into the bracket, this will also give us a negative. Lastly, if we plug in a -2 minus or +3, this also gives us a negative. 3 negatives all multiplied together will end up giving us a negative value. Okay, let's plug in 1 to this. -1 will give us a negative. -1 minus 5 is also negative. -1 plus 2 is a positive. Negative times negative is positive times positive gives us a positive value for this interval. So we have in the first region where it's less than 2, this is where the graph is below the x-axis. When it's between -2 and 0, it's above the x-axis. Now we want to go into the next one where x is 1, it's positive. Where we have 1 minus 5, this is negative. 1 plus 2 is positive. This is going to give us positive times negative is a negative. So we want to make sure we put in a negative for our last one here. And then if we take 6 for x, that's a positive. 6 minus 5 is positive. 6 plus 2 is 8, which is also positive. Therefore, this is a positive region. Where are the regions which the graph is below the x-axis? It's where it's negative here and here. So we need to summarize this as a solution. And then what I'm going to do is I'm going to encourage you to draw the graph here. So therefore, here's what our solution will be. X cubed minus 3x squared minus 10x is less than or equal to 0 when we have x is less than or equal to -2, or where x is between the 0 and 5. So we're going to say 0 greater than or equal to x, which is less than or equal to 5. There is our solution region here. Perfect. And again, just to reemphasize that, we look at this and we're like, hey, it's negative between these two, and then it's negative anytime it's less than that 2 for the x-intercept. Because we always describe it in terms of the x-intercepts create kind of these like boundaries or these regions in which we have, and you can even consider it, instead of regions, intervals might be even the more appropriate terminology. Now, I'm just going to provide you a rough sketch of what this cubic function looks like on the right, just so you can see it, because we've talked a lot about graphing these. You could put this into your graphing calculator, but here's a rough sketch of it. So off to the side, I'm going to draw in the x-intercepts at -2, 0, and +5. Now, the graph might follow a very rough shape of this. This isn't super accurate, but it might do us a little bit of justice. It's going to come up. It's going to go below. It's going to return
back above up here. Arrows on the end. Now let's fill in our values here. This x-intercept was -2, this was 0, this was +5. Where is it that the graph is above or below the line? It is below the line or less than or equal to 0. Anytime it is less than or equal to -2, we see that the graph is below the x-axis. Where else is it below the x-axis? Between 0 and 5. So we're going to also highlight this region here. Or this interval might be the more appropriate way to look at this, because we're thinking about the x values that represent where the graph is below the x-axis here, or less than or equal to 0. Awesome. This is where you're going to want to move on to your assignment. There is a very sharp difference and contrast between 2 variable quadratic inequalities and 1 variable quadratic inequalities. One describes regions, the other one describes intervals of x that represent certain above or below situations for the graph. So it's really important that you do some practice problems just to distinguish that difference and get some practice writing these solutions. All right, good luck with your practice.